Hi everyone, this is my talk. It's based on final year project I did as part of my degree. So the talk is orbit modeling of the International Space Station using symplectic integrators in Python. And I was even just thinking, completely unintentional now, I wasn't able to look into the future or anything like that, but I think this is pretty current, considering I think a Russian segment, brand new Russian segment went up to the International Space Station, but I think they had a bit of an issue with it. It was firing its thrusters and it was kind of spinning it and doing all other kind of crazy stuff. So I suppose it just kind of proves the importance of this kind of stuff. So without further ado, we'll get underway. So yeah, I'm Ben. I am a recently graduated student of maths and physics here in UL. So I've gone to UL for the past 4 years. That's my my mug there on the left. Actually, it's quite an old photo. Actually, now that I think of it, that was me before I went into college, and now I'm just finished. So this is a bit weird, but yeah. So like I said, the talk is based on my final year project, which was primarily centered around the laws of planetary motion and using different numerical methods and techniques to describe how to basically describe the orbit of a satellite using maths and figures, I suppose. So leading on from that, I'm going to be beginning a master's degree in space science and technology at UCD this coming September. So if we move on from that, so basically the talk outline is I'm going to talk a little bit about what symplectic structures and symplectic integrators actually are. What do they do when we actually apply them to a problem such as this, trying to describe the orbit of the International Space Station? And then I'm going to talk a little bit about GMAT, which is a program that was developed by NASA and a few private industry partners, which is used by them for, I suppose, their own space missions and describing the orbits of satellites and space junk and just about everything else that's floating around up there and how they keep track of that all. So kicking off with hard sums and symplectic structures. So basically, I suppose the question on everybody's lips is, what are symplectic integrators? And if I was to give a short but brutal answer, it's a lot of hard maths. So basically, symplectic integration schemes, as they're called, are usually used when we're dealing with a system that's called a Hamiltonian system, which basically means that it can be described by these equations called Hamilton's equations. And from that, we're able to derive the Hamiltonian, which is this equation here. And effectively, the Hamiltonian is basically just a fancy way of writing the energy of the system. So we have these two terms in the equation. We have this term here, which is the kinetic energy, and this is the potential. I see Mark raised his hand. I'm just wondering if he has a question. There's nothing in the chat anyway. So
no, Mark is muted, I think, at this moment. So
okay, perfect. So we have the kinetic energy here, which is basically the mass of whatever satellite you're trying to I suppose trying to describe, times its velocity squared, all multiplied by a half, minus the gravitational constant times the mass of, I suppose, whatever body it's going to be orbiting, in this case the Earth, times the mass of the satellite again, all divided by the radius of orbit from the center of that body, not just, I suppose, from the ground, as we would kind of think of it on the surface of the Earth here. So moving on from that, as this system of basically our Earth, say, and the space station would evolve in time, it will trace a trajectory in what is called RV space, which is also called phase space, which is basically, if we were to plot the distance on one axis and the station's velocity on the other, and if we had two vectors within that, so I don't know if you can see my camera there, if we had two vectors like that, and we basically projected them into RV space, we end up with a vector function here, which is defined by all of this stuff, and basically it's a little bit of vector calculus. So basically we're taking this term here, which is basically the area of the parallelogram defined by those two vectors, if you were to project them out. And basically, yeah, it just represents the area of that parallelogram, which is basically cast out into phase space. And that parallelogram is referred to as a linear symplectic structure. And then if we solve Hamilton's equations, which I briefly mentioned earlier for this system, we generate what's called a phase flow, which maps the initial point of the trajectory, which I suppose we just denote R0 and V0 at t is equal to 0 to another point, Rn and Vn at t is equal to Tn. So basically, if it was at a given point at t is equal to 0, and then using the phase flow, we're able to kind of cast that point out further into another instance in time, say, in this case, maybe if n was equal to 5. So if we wanted to go 5 seconds into the future, we could use the phase flow to kind of like see where our space station would end up 5 seconds time. So then basically, if we take the Jacobian, which is basically kind of like taking, I'm not entirely correct, but I suppose it's an easy way to think about it. If you wanted to take the derivative of that phase flow, which is the Jacobian, we see that it satisfies the relation. So basically, if we're to apply the Jacobian to the two vectors R and V, we see that the area of that parallelogram is the same as the area of the parallelogram we had in the beginning. So basically, like I said, that basically just produces a new pair of vectors. And if we were to create a parallelogram based on those two vectors, we see that the area of that parallelogram is identical to the one we had at the start. And I suppose naturally this proves to us that the area of that parallelogram that we were talking about does not change no matter how far into the future you go. So we say that the linear symplectic structure is conserved. And then that leads us to this kind of funky definition. You don't have to worry about it too much. I'm getting all the hard maths out of the way at the start. So we can say that a function in phase space is symplectic if and only if it satisfies this relation. So if we have the phase flow for a particular symplectic function, I suppose, and this is kind of the test to see, well, is it symplectic? Isn't it symplectic? And this J is the same as this J that we had back here. So then while they conserve the linear symplectic structure, which kind of gives them their name, they don't technically conserve energy. So I suppose there's the principle of conservation of energy that most people would be familiar with, which is energy cannot be created or destroyed, but can be converted from one form to another, say between kinetic and potential and vice versa. So the thing about symplectic algorithms, symplectic numerical algorithms at the very least, is that they don't conserve energy. But I suppose the thing that kind of makes them worthwhile using, despite that fact, is the fact that the energy, even though it does change, it drifts very, very slowly, rather than if we were using a non-symplectic integrator, which would mean the energy would change very, very quickly, and then the whole system would be going haywire. And obviously, we don't want that. So why are they important? So basically, the conservation of the linear symplectic structure, like I said, it makes them ideal for long-time integration, which would be required in orbital mechanics, say. So, I mean, if you're trying to keep track of a spacecraft for, I don't know, if it's just kind of coasting through space for maybe a month, that's why you'd want to be using a technique like this, because obviously, if you're trying to track where this thing is at maybe an interval of maybe 1 second or 5 seconds, or, I mean, only a couple of seconds. I mean, a month is a lot of seconds. So technically, that would be classed as long-time integration. And obviously, I suppose when the wrong method is used, we can see how things go wrong. So here is an excerpt from a paper by two guys called Patrick Choi and Evan Anzalone, I think. And they basically described what happened with the Mars Climate Orbiter, which was a NASA mission back in 1998. And it had traveled 670 million kilometers to Mars. And then a trajectory area of only 150 kilometers squared basically ended up writing off this entire project, and that error was tiny. It was equivalent to 0.00003% of the total distance traveled by the Mars Climate Orbiter. So obviously we need numerical methods that are accurate, stable, and fast. And because the area of that parallelogram, the linear symplectic structure, is conserved, these methods tend to offer, I suppose, the best combination of these, making them ideal for use in orbital mechanics. So getting all of the shock and the hard maths out of the way, I suppose that's kind of more, maybe if you're kind of more into the nitty gritty and the maths behind it, maybe you would have taken something from that. But I suppose for the rest of us, where we're kind of thinking, okay, grand, we can kind of wax lyrical about all of the sums going on in the background, but what do symplectic integrators actually look like when we try to apply them to trying to model the orbit of the ISS? And so moving on with that. So basically, this is the orbit of the ISS using what's known as an SGP4 model, which is kind of the gold standard in orbital mechanics. It was developed by, I think it was developed by NASA in the 1950s and 1960s, and it's been kind of iterated and improved upon since then. I think there was a Python package for it called SGP4, and I ended up using that to basically generate this plot here. And basically taking the initial Keplerian elements, which is basically just a coordinate system from NASA's Human Spaceflight Trajectory website. I started with the space station at this time. So the coordinates that I was given correspond to that time, and that was taken from the same paper by Anzalone and Chai. So like I said, I basically kind of consider this the exact solution. And like I said, it was running a script based on the SGP4 library in conjunction with a 2-line element set, which is a way of designating different spacecraft. I think that's managed by NORAD, and I just used the 2-line element set that was available from NORAD for the International Space Station. So this is for 5,630 seconds, which is roughly equivalent to 1 full orbit. So that's about roughly 90 minutes, give or take, which is about the amount of time it would take for the International Space Station to go around the Earth once. So then if we return to symplectic integrators and what we're trying to do, these are the 3 equations that we need to solve if we want to model the International Space Station's orbit. We need to solve them all together. So it's no use solving one and then leaving the other 2 unsolved. We need to solve them all at the same time. And the fact that we have x2 and x3 in this one here, and then x1 and x3 in this one, and even though this is a derivative with respect to x2 and same down here, it makes them quite messy. And that's why numerical techniques are very, very useful for solving these kind of equations. It can be solved exactly, so we can find a solution to this in the same way that you could find 2 + 2 = 4, to use an easy example. You can find an exact solution. But it's very, very difficult. So rather than that, we use kind of numerical techniques where rather than getting 2 + 2 = 4, you might get 3.9999999, which is pretty close. And I suppose for the sake of modeling spacecraft, that's good enough for most people. So anyway, to kind of explain these terms, x1, x2, and x3 are just 3 different coordinate systems. So if we had like a coordinate system here, this might be x1, x2, and x3, and then here we have G, which is the gravitational constant, which I think is, I don't know, it's 6.67 × 10⁻11. I'm not entirely sure what the units of that are off the top of my head. The mass here is M is the mass of the Earth. And then basically, like I said, the Keplerian elements that I got from NASA's Human Spaceflight website, I transformed them into a Cartesian state vector, which is just an easier coordinate system to work with in terms of it's 6 different coordinates. So you have x1, x2, and x3. And then you have x1 dot, x2 dot, and x3 dot, which correspond to the velocities in the x, y, and z directions. You can see by the units here. So we have meters here. So these are distances, and these are velocities. So basically, moving on to our first symplectic method we have here. This is called the velocity Verlet method. So we have 2 different equations here. One for finding the distance of the displacement, the position of the International Space Station at any point in time. And here we have the equation for finding the velocity at any instant in time. And obviously these are linked, so we'll need to sub the velocity into this equation. So it's no use just relying on this one alone. And f of x and n and t of n represents the acceleration of the station at t = tn. And h is the time step. So as in, if you wanted to model where the station was at, I suppose in this case, I chose every 5 seconds, say, I let h = 5, as I did here. And I just used the same initial conditions that I had on the previous slide. So all of those distances and the velocities I subbed into this equation here for each of the x, y, and z directions. And this is what I got. So this looks pretty good. You look at this and you think, well, I'm pretty much staring at the same diagram that I saw 2 slides ago. I can't tell any difference. So it looks like we're in good enough shape. So I suppose to look at it in a little bit more detail, if we looked at it in 2D, we find this, and this almost looks like a perfectly stable orbit. So we're thinking, great, we look like we might be on the right track here. So it's definitely a decent start. So we find that when we zoom in to take a good look at the orbit here, we find that the International Space Station over the course of 33,780, which is about, I don't know, 6-ish, roughly, I suppose, roughly 6 full orbits. So it's about, I don't know, just under about a third of a day, so about 8 hours roughly. We find that it spirals outwards by about 25 meters, which I suppose on the orbit of the ISS, which orbits above at about, I don't know, 400 odd kilometers above the surface of the Earth. It's not over from the center of the Earth, but so yeah, from its kind of point of reference, its orbit, 25 meters is tiny. It's virtually negligible. So this is a good start. But moving on from that, we kind of wonder, can we do better? So obviously it seems to work quite well, the velocity Verlet method. But the thing is, in reality, though, the ISS doesn't spiral outwards like that did. So if we have another look at this, we see that this would spiral outwards rather than spiraling inwards towards the Earth, which would happen in actuality because I suppose gravity of the Earth would be attracting the ISS. And also there is an element of atmospheric drag that will be kind of slowly dragging it towards the Earth. However, trying to model atmospheric drag, we have to deal with a totally new set of equations. They're very, very difficult to solve. And I'm wondering, can we cheat a little bit? Can we find a method that accounts for the fact that the station would spiral inwards without having to completely modify those equations we saw a few slides ago? So can we get, I suppose, the mathematical equivalent of a free lunch? And I suppose the best answer I could give is sort of. And even if we can, is there more than one method that could do this for us? Can multiple symplectic integration systems, could they work well for this? And with that in mind, how do we find the best one? So I suppose to answer that, the main way to do it is just trial and error. So we try a few different symplectic methods and find whichever one works best. So just taking a stab at one of these methods, this is the implicit midpoint method, which is described as follows. So this is the equation we use to find the position at any point in time, and this is the velocity. However, if you take a look at this, we see that Vn plus 1 here is equal to this. So obviously we can reduce this all to one equation as follows. However, we see that we need to get xn plus 1 on this side, but we also need to sub it into the acceleration, whatever function we have here that describes the acceleration. We have to sub xn plus 1 in here. So that complicates things. So it depends on whatever function we use to describe the acceleration. And in this case, it's quite complicated. So, I mean, if it was just f of x was just equal to xn plus 1, we could, I don't know, do a little bit of algebra to get things on the right side, and we could kind of simplify from there. But sometimes that isn't always possible. So we need to use a root finding algorithm, such as fsolve, which is available in SciPy. And we need to solve for xn plus 1 at each time step. But obviously, if you need to do this at every single time that you want to solve for the station's position, this can get quite computationally expensive, and it can kind of slow things down. So what do we end up with? We end up with a slightly different diagram here. We can see that the behavior is qualitatively correct in the sense that it gets a small bit closer to the Earth every time. Well, I suppose not really a small bit, but it gets closer to the Earth, but the orbit decays quite rapidly. So we wonder, okay, this is sort of okay, but it's not fantastic. So again, looking at the 2D projection that we had on the previous slides, we see, okay, how good or bad is this? How quickly does the orbit decay? So for 32,780 seconds, we see that the ISS spirals in by 1.2 by 10 to the 6 meters. So we find that if we start at the average orbit, the average altitude even, 407 kilometers, we find that the ISS would collide with the Earth after only 3 periods. So it would only go around the Earth 3 times before it would smash into the Earth, which isn't ideal. We don't want our space stations falling out of the sky and potentially hurting someone. So we see that this method is definitely the wrong choice to use. So we need something that's a bit more accurate. And with that, we move on to the Chin-Chen 4A method, which was developed by Chin-Chen way back in 2003. This is their 4A method. They have developed a host of other methods that I looked at as part of my final year project. Then there's the 4B, 4B dash, and then the C and 4D. I don't know. So this was probably the most straightforward. So I looked at this here. It's definitely a bit more involved than the other two methods because we have kind of fractional time steps. It's not v is equal to n plus 1, n plus 2, n plus 3, and so on. We kind of split up the time increments into fractions of either a half or a third. And if we are to find the derivative of the acceleration function, which is technically called the jerk, we need to differentiate the governing equations a few slides ago that we saw there implicitly, and the symbolic solving tool such as SciPy definitely made this a lot easier. I can remember with my final year project having to try and do it by hand and just almost tearing my hair out because it was just so involved, got so messy. So thankfully SciPy was there to definitely do a lot of the heavy lifting. And then if we go back to this here, we see it definitely looks a lot better than the implicit midpoint method that we have here. So again, we ask the same question, how quickly does this decay? And we see that it does decay by a bit more than the velocity Verlet method, but obviously this is in the right direction because we want it to decay inwards rather than outwards. So it decays by 1.5 by 10 to the 5 meters over the course of 6 periods, which is less than the amount by which the implicit midpoint decayed over the course of a single period. So obviously this is a lot better. It's not perfect though, in the sense that the orbit would decay fully after about 6.28 orbits, which is about the course of a day. So it's not 100% there yet. There's still a lot of factors in play because thankfully, if I look at the window, I don't see any international space stations rushing towards us just yet. So obviously it's a good improvement, but we're not quite there yet. And I suppose the accuracy could be further improved by tightening up the time step. I used 5 seconds for all of my methods, but if you wanted to use maybe like 0.01 second, it would probably be a lot more accurate, but it would end up being a lot longer. So to compare that with a non-symplectic method here, we have the RK45 method from SciPy, which is not symplectic, and it basically uses what's called the dormant prince technique, which uses 2 algorithms, which are Roman Cotta methods, which is basically just a class of numerical solvers, and it uses the 4th and 5th order Roman Cotta methods, and basically takes the difference between those as the error, and it will keep going until the difference between those 2 methods reaches a specified tolerance, which is usually decided on by the algorithm. And basically, I suppose if you wanted to look up Dorman Prince's paper from 1980, if you wanted to get into the nitty gritty of that. And basically, if we were to apply a non-symplectic method to this problem, we see that it behaves much more, I suppose, drastically. I suppose if that's the correct word you want to use here, on how it would model the behavior of the space station. So like the implicit midpoint method, this solution decays very, very quickly if we were to apply to this problem. And I suppose the point I'm trying to make here is that non-symplectic methods, the errors that result, they compound very, very rapidly, leading to incorrect results, kind of like the Mars climate orbiter example I gave a while ago. So the orbit decays by 1.55 by 10 to the 6 meters over the course of 8 periods. So that would mean that in just over 2 periods, the orbit will fully decay, which means that this is even worse. If you thought the implicit midpoint method was bad, this is much worse. Like this won't even get around the ear twice before it ends up smashing into it. So I don't think it would instill an awful lot of confidence in anybody if you were using this method to describe the orbit of the International Space Station. You'd be telling people to run for cover, which thankfully they don't have to. So I suppose to kind of summarize what we have to date, in general, the symplectic integrators tend to outperform non-symplectic integrators when you want to use them for orbital mechanics. And like I said earlier, if you wanted to kind of shrink the time step, I used 5-second time steps. But like I said, if you wanted to use maybe a fraction of a second, say maybe 0.01 or 0.0001, or if you wanted to throw in however many zeros you get there, you get an even more accurate solution. But obviously, you're computing more points if you're kind of making the time step smaller. So this would cause your code to have to run for a lot longer. And I know this is a Python Ireland group, so I mean, there might be a bit of shock here, but compiled languages, maybe C or even Julia, might perform these computations more quickly than Python. However, I suppose another question you could ask is, could other programs be used with Python rather than having to completely scrap Python? to try and solve these problems? And the answer is yes. And that leads me to the final section, which is GMAT. And so basically, what is GMAT? It is a general mission analysis tool, which is a software package developed by NASA and a few private industry partners. So this is basically just here on the left, we have pictures of what you would see if you wanted to use GMAT. So we have here if you wanted to use the GUI, and then this is the scripting interface. They're basically kind of built in, kind of one and the same. It was first released in August 2007. It's completely open source. It has been ever since. I'm pretty sure they have a GitHub. So if you wanted to maybe contribute to it or log errors or kind of play around with it, you could, I don't know, open a pull request there and say, oh, hey, here's a problem that I managed to solve for you guys. But GMAT was approved for operational use in 2013 during the ACE mission. So this is the same software that NASA use, which is, I think, is quite interesting. The fact that NASA have made the software that they use for monitoring their missions, they've made it completely open source. And it was back in 2013, they did that with the ACE mission. And like I said, there is a graphical user interface and a scripting interface available. And if anyone is interested in actually trying to learn how to use this, there's a full tutorial available on GMAT YouTube channel, which is, I don't know, maybe there's a couple of hours worth of tutorials there if you wanted to kind of get your hands dirty and kind of fiddle around with this. So you're probably wondering, okay, it has a scripting interface, but which has a syntax which is similar enough to MATLAB, but you're probably wondering, why would I bother learning a new language just to use GMAT? However, GMAT also has APIs for Python, MATLAB, and Java. So you can call Python, MATLAB, or Java, or I suppose depending on which API you're using natively in the scripting interface. So here's a very simple example here. If you wanted to create two variables here, just using kind of GMAT syntax, you can call on, this the SignH function here from Python. So this SignH function is being called from Python rather than from GMAT. This isn't a GMAT function. This is just calling a Python function to do whatever heavy lifting you want it to do. So I suppose what kind of makes GMAT so great, you wonder? I suppose, like, couldn't we just do this in native Python? And to a certain extent you could. However, using the 5-second time step that I used for all of my different methods, GMAT had a mean runtime 3.47 times faster than native Python. And obviously, these are the orbit view and the ground track are, I suppose, very powerful. They're, I suppose, a lot more specific to what you might need if you were working with orbital mechanics than what you might get in matplotlib. And it works well for spacecraft in low Earth orbit, but also GMAT can be used for interplanetary missions. So I've seen people use GMAT to describe maybe if you wanted to send a probe to Mars or maybe to Venus or something like that. GMAT works perfectly for those instances as well. So in order to get Python and GMAT to talk to each other, how do you get it to work? So you basically code up your symplectic integrators in Python. So whichever method you wanted to use there, say, you basically just write a Python file with all of those in it. And you basically just make that a module with all the different functions you might want. And then within GMAT, you call that module, you save it to, I think there's a Python folder within, I suppose, the GMAT file structure there that you can, it works as like the side packages folder, if anyone's familiar with that and working with custom Python modules. GMAT has its own kind of equivalent folder that you save all your modules to, and then you can call it within GMAT's kind of command line interface using Python dot, I suppose, the module name and then the function and then whatever arguments are needed for that function. You save and run the script and hey presto. So if I wanted to use the Chin-Chen method that I was talking about a while ago, this is kind of the stuff that I would be doing with it. So Python.symplectic integrator / Chin-Chen for a, and then this is basically, I've called the Python integrator, but it's not happening. None of that computation is happening in GMAT. That is all being done under the hood by Python. So behind the scenes, this is what we get. This is the integrator itself here. And obviously it took a bit of trial and error to actually get GMAT and Python to talk to each other, a bit of fiddling around to kind of work through these errors. But it all came good in the end. So basically I have two different comparisons here. So I have this file that was generated by GMAT showing that we have the X, Y, Z, and then X, Y, and Z velocities. And then we see here, if I ran it natively in Python, we have pretty much the same values. The only difference is rounding. So to wrap everything up, I've managed to get Python and GMAT to play nicely together. There's definitely a lot more to be done though. So replacing GMAT's inbuilt numerical propagators, they have a ton of those. None of them are symplectic though. So I'm kind of wondering, could we take advantage of symplectic integrators and build them into GMAT to, I suppose, end up with more accurate results? GMAT also has a Python library called GMAT-Py, which gives Python access to GMAT's propagation and navigation features. So if you wanted to, say, describe how a spacecraft would move, if you just gave it a boost of, I don't know, however long, maybe if you wanted to give it a boost for 10 seconds, see what would that do to its trajectory and the navigation and so on and so forth. GMAT has a bunch of those features, and using GMAT-Py basically ports all of those over to Python so that you can use it if you're more comfortable using Python rather than GMAT. And like I said, there are tons of other symplectic integrators available, loads and loads and loads. If you just Google symplectic integrators and throw it into Google Scholar, you'll find tons of different research papers of people basically, oh, there's this method and that method and so on and so forth. We could test loads more of them, and there's bound to be an even better one out there than any of the ones that I've even used. We could even choose a symplectic algorithm even with an adaptive time step. So I chose H to be 5 seconds for all of my methods, but you could develop a more complex algorithm where H isn't always 5 seconds. So you might be able to integrate kind of a logic into your algorithm where it'll be like, okay, so based on these conditions, what will I choose the time step to be? So it might not be 5, it might be 2.5, it might be 0.01, depending on whatever conditions you manage to incorporate into your algorithm. And I could also try out the MATLAB and Java APIs and see how they compare with Python. So that is that. Thank you all very much for your time. And I'm just wondering if anyone has any questions.
Yeah, I think there was a very interesting presentation, but I think we would need graduates of maths and physics to really be able to ask some sort of questions. So I'm wondering, does anybody from the audience have any questions they'd like to ask you? I'm not sure. I cannot see chat, or I cannot see much happening in the chat. Not sure if anybody asked any questions. Can you see anything, Ben?
Nothing yet, anyway. No.
No. Well, I guess there is no questions for now. I'm just wondering, because you mentioned there Cartesian coordinates, and you were you're converting them from the original values you received. Did you do that through the MATLAB, or you used some online tool for recalculation of the coordinates?
I use Python to do that. I use basically Keplerian is basically, they're also known as elliptical coordinates. So I suppose basically using kind of Kepler's laws, he came up with a specific coordinate system, which is, I suppose, I don't know, there's different ones, like I think it's like the argument of perigee and ascending node, and they have all these different funny names for all different coordinates. And they were all given in the paper by Anzalone and Chai that I mentioned. And I basically just converted those using Python into Cartesian coordinates, because Cartesian coordinates, they tend to just be a lot easier to work with, and most people are familiar with them. So I used Python for that. I suppose Python was pretty much what I used for pretty much everything, apart from a little bit of messing with GMAT. But yeah, it was pretty much all Python doing the heavy lifting.
Okay, that's interesting. Anybody else have any questions in regards to the presentation? How long were you studying your degree? Because this seems like a lot of work and a lot of involvement on your side.
Well, I suppose my degree was 4 years, so I just finished there in May. This was part of my final year project, so this is all work that I did over the course of my last year in college. So,
okay, very interesting.
Thanks.
Yeah, I don't see any questions coming in.
Me neither. It looks quiet on my end.
Yeah. Like I was asking you about the Cartesian coordinates because I have actually surveying background. So yeah, that would be, this type of recalculations would be quite familiar to me. I would just never do them from the Python perspective before, because that was before my programming career. So yeah, I'm touching slightly different areas at the moment. Very good. As I don't have any questions coming in, I'm wondering, can we add anything else? Like, are you going to provide us the PPT file from your presentation as well, or
yeah, absolutely.
with Nicholas?
Nicholas didn't mention it to me, but I could send it on. Yeah, this is just a PDF here, so yeah, I could absolutely send it on. Yeah.
Okay. No, I'm just asking and wondering. You know, maybe somebody's going to be interested in the future to have a look at the presentation that you provided here. You know, so probably it would be a good idea to, if you wouldn't mind, to share it with.
Yeah, absolutely, and I can send on all the source code as well if anybody was interested in that too.
Okay, perfect. That would be phenomenal. Thank you very much for your time. So
yeah,
I think we can finish here. I'm not gonna even try to ask any questions in regards to all of the calculations you did in there. I was wondering earlier on about the errors, you know, because in the beginning of your presentation you didn't say anything about the errors, and then you just clarified it very clearly. And also I noticed that the orbit that you are presenting on the slides, it's not, I mean, it was a 3D visualization of the orbit, but for whatever reason, I had a feeling that the orbit was presented in 2D at the very beginning of, you know, of your presentation. Yeah, but that obviously was not the case. Perfect. Again, Ben, thank you very much.
Thanks very much, everyone.
I wish you a very best of success with your master's degree next.
Thank you very much.
And yeah, I'm sure we're going to see each other on similar webinars sometime in the future.
Yeah, absolutely. I heard sure PyCon Limerick. I mean, I'm local, so I mean that's only over the road for me. So fingers crossed that might get to go ahead.
Exactly. Yeah. Cool. Perfect. Thank you very much, Ben. Thank you very much, everybody.
Take care, everyone. Thanks very much.
And I wish you a great summer, great weather, and great time.
You too. All the best.